Or in this example, we're going to use the second derivative test to find a local extrema. And another way of phrasing the same problem might be to classify all critical points. And a lot of directions don't tell us to use the second derivative test, but we're going to use the second derivative test as an example. So the first thing we should do is we should find there's steps to this no matter what. We need to find f prime of x. We need to find all critical points. And in this case, we could just find the x value, which technically is the critical number. And then we want to use the derivative tests for either first or second, I'm not writing that, tests on each critical point. I'll just shorten that to critical point. So those are the overall steps when you're talking about finding local extrema or classifying critical points. And so the first thing we need to do is find the first derivative. And being very careful with our power rule, when we bring down the 3, the 3's will cancel. So we're left with 2x squared minus 8x minus 42. And here, because it's a quadratic, there are two ways you can be a critical point. One is if the derivative doesn't exist, and one is if the derivative equals 0. In this case, there are no problem spots with the derivative. Quadratic is defined for all x. There's no dividing by 0, all of that. So the only critical points are when f prime of x equals 0. So a lot of these examples are going to be algebra review. And so we want to solve, in order to find all critical points, we want to solve 2x squared minus 8x minus 42 equals 0. And we could go directly to the quadratic formula, and that will work, or we can try and factor. We're going to try and factor this one. And we get 2 times, I'm going to factor out a 2, because that helps me factoring in general. If I have a leading coefficient of 1, it's easier for me to factor. But you could try and factor this directly. Some people are really good at that. So for here, this ends up, I'm not going to go through all the processes of trying to figure out that this factors to 2 times the quantity x minus 7 and the quantity x plus 3. And that will give you a constant term of the minus 27, and the 2 middle terms gives us a middle term of minus 4x. So we have two critical points when x equals -3 and 7, and I listed them in numeric order. Sometimes our homework might make us enter them on the computer in numeric order, so we have to be careful of that. So we have that, and right now I don't care about the full point, I only care about the x values, so I'm gonna wait on the rest. And I said we're going to use the second derivative test. So what's nice about the second derivative test for this one is the second derivative is fairly easy to calculate. There are going to be others where we won't want to do the second derivative. So now we're at the point of using the second derivative test. And so we need to find the second derivative. And being very careful, making sure we're looking at the right one. We are taking the derivative of this guy, so we get 4x minus 8. Now, right now, for the second derivative test, we're not going to do anything other than plug in these values. So we want to figure out, I'll just write it in a different color, f double prime of negative 3. And when I do that, we're going to do, and in this case, remember the second derivative test, we only care whether or not it's positive or negative at that spot. So when I plug in negative 3, I get 4 times negative 3 minus 8, negative 20. We didn't even need to figure out that it was negative 20. The key is that this is less than 0. So we have a spot where we have a horizontal tangent line, and the second derivative is negative, so that means we're concave down. So that tells us we have a situation where we're looking like this. So this gives us a local max at x equals negative 3. If we look at the second critical point, right now it's just a critical number, f double prime of 7. Plugging that in, 4 times 7 minus 8, we get positive 20. The key is that it is the second derivative at that critical number is positive. So we had a horizontal tangent line and we're concave up. So that tells us we have a picture that looks like that. So that we have a local min at x equals 7. Now, if the directions were to find all and classify all critical points, these technically aren't points yet. Those are just the locations. So we have our answer. We have negative 372. How did I find the 72? Plug in, we need to figure out the y value on the function, plugging in negative 3, being very careful, having technology help us if needed. Get 72. We have a local max. And at negative 784 over 3. Again, I plugged this in and wrote it down because I would not have remembered that. Negative 784 over 3 is the y value of this point, and this is a local min. And when we graph this and we adjust our window appropriately, we can see exactly what's going on at these spots. And those are the exact y values for those local extrema. If we go to Desmos and put in our function 2/3 x cubed minus 4x squared minus 42x, we see that our initial default window does not show us the whole picture. So we might need to adjust. And we know that we have some special spots at negative 3 and 7. So we might go from negative 15 to 15. And we had some pretty large negative values, or I guess small. So we might look at going from, negative 700 and even to 200, or maybe even 300. And now we can see the negative 372 local max that we found, and the negative 784 over 3, which rounds to negative 261.33 as our local min. Notice there are other values further away that are smaller, but locally this is the smallest value, and locally this is the largest value.